Science never ends. Welcome to the series of videos about Nobel Prize winners, a group of interesting and inspiring scientists. You must have heard of Albert Einstein, his development of the special and general theories of relativity, his role in the development of the quantum theory, his contributions to our understanding of Brownian motion and the foundations of statistical physics mark him as the greatest scientist since Newton. Let's dive into the world of Albert Einstein. Albert Einstein was born in Ulm on March 14, 1879. Einstein excelled at math and physics from a young age, reaching a mathematical level years ahead of his peers. The 12-year-old Einstein taught himself algebra and Euclidean geometry over a single summer. By the time of age 13, he already had a predilection for solving complicated problems in applied arithmetic. During his vacation, he set to work on theorems, not by taking their proofs from books, but rather by attempting to prove them for himself. For days he sat alone and was immersed in the search for a solution. He even found an entirely original solution for the Pythagorean theorem. In 1896, he entered the Swiss Federal Polytechnic School in Zurich to be trained as a teacher in physics and mathematics, where his remarkable career began. In 1905, a year described as his annus mirabilis, Einstein published four groundbreaking papers. These outlined the theory of the photoelectric effect, explained Brownian motion, introduced special relativity, and demonstrated mass-energy equivalence. Einstein thought that the laws of classical mechanics could no longer be reconciled with those of the electromagnetic field, which led him to develop his special theory of relativity. He then extended the theory to gravitational fields. He published a paper on general relativity in 1916, introducing his theory of gravitation. In 1917, he applied the general theory of relativity to model the structure of the universe. In 1922, he was awarded the 1921 Nobel Prize in Physics for his services to theoretical physics, and especially for his discovery of the law of the photoelectric effect. In 1887, Heinrich Rudolf Hertz observed a strange phenomenon. When ultraviolet light shines on two metal electrodes with a voltage applied across them, the light changes the voltage at which sparking takes place. This was the first time the photoelectric effect was found. Later, scientists defined the photoelectric effect as a phenomenon in which electrically charged particles are released from or within a material when it absorbs electromagnetic radiation. The phenomenon was fundamentally significant in the development of modern physics. What is more important is that it cannot be explained by classical physics. In 1905, Albert Einstein came up with the theory of the photoelectric effect, using a concept first proposed by Max Planck. He pointed out that light consists of tiny packets of energy called photons. The energy Planck's constant carried μ by each tiny packet is proportional to the frequency μ of the corresponding light. The proportionality constant h has been called the Planck constant. The Planck constant is a fundamental physical constant in quantum mechanics. In 1900, Max Planck postulated that blackbody radiation can only change its energy by a minimal increment e, which is proportional to the frequency of the associated electromagnetic wave. He was able to calculate the proportionality constant, which is honored with his name, from experimental measurements. When an electron in some material absorbs the energy of a photon and gains more energy than its binding energy, it is likely to be ejected. Electrons emitted in this way are called photoelectrons. The maximum kinetic energy max of an electron is where phi is the minimum energy required to remove electrons from the surface of the material. It is called the work function of the surface. If the work function is written as the formula for the maximum kinetic energy of the ejected electron becomes the kinetic energy is positive, and μ is greater than μ0 is required to generate the photoelectric effect. Frequency μ0 is the threshold frequency for a given material. Above this frequency, the maximum kinetic energy of photoelectrons, independent of the number of photons and light intensity, increases linearly with frequency. Einstein's formula, no matter how simple, explained all the phenomenology of the photoelectric effect and had a profound impact on the development of quantum mechanics. Now, we need to explain why the explanation of Einstein's theory on the photoelectric effect is so important, that it deserves the Nobel Prize. Classical physics described light as an electromagnetic wave at that time, and everyone believed this to be true. Imagine some beach balls sitting on a dock that extends out into the ocean. The dock represents a metal surface, the beach balls represent electrons, and the ocean waves represent light waves. If a single large wave were to shake the dock, we would expect the energy from the big wave to send the beach balls flying off the dock with much more kinetic energy compared to a single, small wave. Thus, physicists expected that waves hitting the dock more frequently would result in more beach balls being knocked off the dock compared to the same-sized waves hitting the dock less often, but the observed results were completely at odds with the predictions based on the classical description of light as a wave. William Thomson once said, "Physics was finished in 1900 but two dark clouds exists. One of them came at that time." Einstein proposed an entirely new model to explain the phenomenon, which eventually opened the door for modern physics. There is no doubt that Einstein's greatest contribution is the theory of relativity, although he was not awarded with the Nobel Prize for this. This theory is one of the most significant scientific developments in all of history, and has generally changed the attitude of scientists towards space and time. The theory is deceptively simple. First, there is no absolute frame of reference. Every time you measure an object's velocity, its momentum or how it experiences time is always in relation to something else. Second, the speed of light is the same no matter who measures it or how fast the person measuring it is going. Third, nothing can go faster than light. This theory also showed how objects behave when they reach the speed of light. For example, if you can see a spacecraft traveling at 80% the speed of light, you see the spaceship 40% shorter than average. If you could see from the inside of the spaceship, everything outside would be seen in slow motion, and time would pass more slowly. As the speed increases, the crew of the spaceship would reach old age later. In the field of physics, relativity improved the science of elementary particles and their fundamental interactions, along with ushering in the nuclear age. With relativity, cosmology and astrophysics predicted extraordinary astronomical phenomena such as neutron stars, black holes, and gravitational waves. The really cool effects of relativity, such as time dilation and length contraction, don't show up in our everyday lives, as they tend to happen at speeds close to the speed of light. However, there are many things that couldn't happen without general relativity, such as GPS and electromagnets. She was a physicist and chemist who pioneered experimental research into radioactivity, developing novel techniques for isolating radioactive elements and putting them to practical use. She was the first person to win a second Nobel Prize and is also the only Nobel Prize winner. Who is the mother of another Nobel Prize winner? Do you know who is she?